All right. So let's continue where we started last time. So let me just quickly recap what we did last time, yesterday. So the main question that we were concerned about was this uh, whether there is a constant space algorithm for the majority function, where the majority function is designed in the following way. Uh, basically, majority it's all the set of all binary strings where the number of ones is greater than the number of zeros. And then we had a small discussion about what do we exactly mean by a constant space algorithm. And so here again, like we recall that, like, finite state automata are like traditionally what are considered like an example of a constant state algorithm. I mean, constant memory algorithm. And we also saw quickly that using majority shouldn't be one of those languages which is recognized by a finite state automaton, right? So majority is not a regular language. And okay, uh, and then we went on to say, okay, so to look at these other models of computation, so-called non-uniform models of computation, where you give the algorithm designer the power to, like, not just have like one algorithm which solves all solves the problem on all input lengths, but it could potentially have like different a completely different algorithm for that works for a different input length. Yeah. And so we saw that these non-uniform models are slightly weird. uh, they can they can do they can compute uncomputable, or it can compute all functions essentially, right? And all Boolean functions, let's say. And so one particular non-uniform model which we saw was this branching program, which is a natural generalization of a natural non-uniform variant of this finite state automaton. So what is it? So we defined it. So defined the branching program as, like, I mean, basically via a DAG. You are given a DAG, and then with the distinguished source and sink vertices, and your this graph, the edges are labeled according to variables, right? Like labeled by variables, and it reads a variable along its edges, and when you have a particular input string, let's say x1 to xn, and depending on the setting of this input string, this defines path or a set of paths in the branching program. And if there is an st path on this particular input string x1 to xn, then you accept this input. Otherwise, you reject this input. Okay? So this is the model. A natural, I mean, the acceptance is based on reachability on a DAG. And there are two measures that we saw, measures of efficiency for this model, and they were basically length and width of the branching program. Length is the the longest path between longest ST path basically, and width is, well, you talk about this notion of this layered branching program, and any branching program can be layered. And the number of vertices in the largest layer essentially is the width of this branching program. Yeah. And we also saw that, these branching programs of constant width can compute any Boolean function, albeit might require exponential length. And this branching program width, in fact, we saw that it captures a notion of space, right? Like, just as how finite automata is one way of capturing space-bounded algorithms, this branching program width would capture a notion of space. And in fact, we made this very precise. One thing I sort of didn't mention very clearly last time is when I said this log of this branching program width is, in some sense, it captures a space usage of your algorithm. Let's say, uh, but here I think I was a bit hand wavy last time. So, but the main idea here is that whenever I talk about an algorithm here, I'm talking about a Turing machine implementing this algorithm, and from that Turing machine, and using that implementation, we were deriving this connection between the log of this branching program width and the space usage of the Turing machine. I didn't explicitly mention Turing machine last time. And in fact, so even though we're talking about a non-uniform model of computation, in fact, if you want to really realize this connection, you have to have like some sort of uh, uniformity measure. And in fact, uh, I will talk about uniformity more in more detail tomorrow. Uh, but it's in some sense like, sort of take this non-uniform model and then say that, well, even though you allow different algorithms for different input lengths, it's not like, I mean, you somehow say that there is one single algorithm which can generate a description of this these different programs. Yeah. So in some sense, you're recapturing this back this notion of uniformity. I mean, whatever uniform algorithms means. Yeah. And in fact, we saw that uniform branching programs of polynomial size is exactly this class called non-deterministic log space, NL for short. Yeah, so much for branching programs. So today we're going to see we're going to move to a slightly a new topic, and this is yet another non-uniform model of computation, and these are going to be what are called Boolean circuits. All right, so Boolean circuits. So what are these? What is this computational model? It's again, I mean, like in the case of branching program, it's a non-uniform model. So, you you take your language L and you look at slices of your language and ln, and so your Boolean circuit now again is going to be a family of algorithms, one for each input length, where ln is decided by Cn. Yeah. And okay, so what is exactly a Boolean circuit? It's again a DAG. Like by definition, structurally, it's going to be a DAG, right? So let me draw a DAG here. So here I'm going to draw a DAG in a slightly different way from last time. So it's a DAG where at the bottom, and I'm going to call these things leaves. These are going to be labeled with variables and maybe some constants 0 and 1, which you can use freely in the middle. And so these are what I'm going to call leaves of my DAG, right? And and the nodes here, I'm going to call them internal vertices or internal nodes, and they're going to be labeled by some Boolean function. In particular, the only function that we are going to look at is or and not. So they're going to be labeled with these gates. Yeah, and naturally every gate computes this function, whatever this function labeled here. So for example, this gate computes the function x1 and x2, right? And every gate computes a function of its children, because I mean, or rather it's yeah, wherever the incoming edges are coming from. So for example, in this case, this is going to this node here, maybe I'll label it as an OR. It's going to compute an OR of these two gates. If I call these gates G1 and G2, then this node here is going to compute G1 or G2. And naturally, you have a computation flowing in this way, and finally you have some output gate, and this output gate would be either an AND or OR, whatever it is. And here you compute the function. Right? Basically, here you compute some function fn from uh, 0 to the n to 0. Okay, and this is called the output gate of the circuit. Right? So there are a few parameters I would like to mention here. So I'm going to call. So again, I already defined input gate, which is these variable. These are the leaves, right, labeled by variables and constants, and internal gates, which are labeled by Boolean functions like AND and OR. And then we saw an output gate. Now, So here's the definition. Like I'm going to call as define this notion of a fan-in of a gate, and fan-in of a gate is nothing but number of. Okay, and all these edges I'm going to call, these are going to be called wires. I'm going to call them wires. Yeah, and the number of incoming edges into a particular gate is called the fan-in of this particular gate, right? So in particular, for example, this gate, the fan-in is 2. And similarly, as fan out, what I mean by fan out is number of edges, outgoing edges. Okay. For example, in this, if you take this OR gate, again, it has fan out 2. So this AND gate, it has fan out 2. Okay. In some sense, fan out, so fan in is sort of like, I mean, there's not special meaning, but like if you want to look at fan out, like you can think of fan out as number of times an intermediate computation is sort of reused, right? Fan out measures uh, how much you can reuse a computation that you've already performed. All right, so I hope the definition of this model is clear. So, and yeah, so, and you say a circuit family Cn decides, language L if and only if, uh, when Cn on an input X is evaluates to 1, because it's computing a Boolean function, if and only if X belongs to L. Yeah, where X is a length and input. Okay, so there are a couple of easy normal forms that I would leave as an exercise. So if exercise, notice that any circuit without any Boolean circuit here, like this one above, uh, can be assumed uh, to have fan in and fan out 2. Let's say fan in 2, and you can also, I think you can also make fan out 2 by using the similar technique. You can just probably think about how to do this. And for example, you can always assume that variables are always at the leaves. Variables are inputs, always at the leaves. And what else? Like you can also assume that all the negation gates are only at the leaves. Yeah, again, it's an easy exercise using the Morgan clause. So negation gates are only at the leaves. Yeah. So the internal gate. So in particular, you can think of your circuit as at the bottom having not just x1 to xn, but also x1 bar up to xn bar, and then you can just, the internal gates are just and a lot. This normal form you should be able to always get for any circuit. And there are 2 measures of efficiency associated with the circuit. Measure of efficiency is size and depth. So what is the size? Well, there are 2 measures that you can use for size. Either you can use the number of wires in the circuit or the number of gates. And these are just, if you don't care about polynomial factors, these are just, like a quadratic factor array. So you can always, you can pick one of them, whichever you like. And the depth of the circuit is the is the length of the longest leaf to root path. Yeah, and this is going to be the depth of the circuit. So if you recall last time I said, like, one measure, something about different resources that you can sort of that you can measure in your computation, and one of them I said was parallelizability. And this circuit model exactly actually captures, in some sense, how parallelizable your computation is. Okay. In general, I mean, of course, if I gave you a circuit of size S, uh, again, in general, uh, in general, a circuit of size S has depth S, right? You can't, I mean, it need not be parallelizable. So, but often we'll be interested in circuits which are like short compared to, I mean, whose size is small. Sorry, the depth is small compared to the size. Yeah. Small compared to size. So for example,
why do you say in general? It is in the worst case, yeah?
Yes, in the worst case, if you don't have any restriction, then your circuit can have depth. If it has size S, it can have depth also S, right? Because you can have like, it need not. I mean, you can have like a long path, right?
Yeah,
Not in general. What I mean is, like, if you didn't place any restriction,
yeah.
in a general circuit, yeah, the size and depth are almost could be of the same order of magnitude,
Yeah.
right?
And I have a question. So
Yeah.
you said so in branching programs, we said it
Yeah.
was the interesting measures were width and length, and of course size also.
Yes, yes. So yeah, so yes, last time I forgot to mention the size is just some sort of like width times length, right? In the
Length, yeah,
at most, yeah.
yeah. But in here you are
Hmm.
considering only depth and size. So
Yes.
why width is never interesting?
Oh, that's a great question. Like, you can also consider width. People also study width. It's just that yeah. So you can also consider. I mean, so the thing is, you cannot simultaneously bound both width and depth. Then you don't get anything interesting.
Okay.
Often. So either you bound depth or you bound width. So it is interesting to study width in the case of circuits.
Uh-huh.
And people indeed study bounded, these are called, bounded width circuit. Maybe I'll talk about them a little bit later.
All right.
When
Okay.
I bounded, so you can say bounded width or depth uh,
Uh-huh.
circuits, both are interesting. Yeah.
Okay.
Yeah.
All
Good,
right.
great question. Yeah. Thanks. Yeah. All right. So let's yeah, so yeah, in general, the circuit of sizes can have depth, yes, but we're going to like look at the regime where we are going to be interested today and tomorrow. Usually, our size is both are going to be measured in terms of the number of variables. So the nth circuit family, ideally, we would want it to be something like n to the odd one polynomial size. And but the depth, we are going to often be interested in things which are like either constant depth, so yeah, or or depth something like logarithmic, like log to the kn depth. These are like sort of what is going to be interesting for us. In fact, I'm going to just like immediately define a couple of complexity classes parameterized by these two measures, size and depth. Maybe also we can see class based on width. Uh, so so here are page. So here are two complexity classes, circuit complexity classes. You might have seen P, NP, and G space, and so on, which are classes based on Turing machine, but this is going to be based on circuit class, so Boolean circuit. So it's called circuit complexity classes. And just as how, like, in Turing machine setting, like the resources that you cared about were time and space, and you restricted them and then got complexity classes. Similarly, here the measures that you care about are size and depth, and you're going to restrict them. In fact, in particular, we're going to restrict depth and get a couple of classes. So we're going to define two families of classes, and this is called AC and NC. AC is what is called an alternating class, uh, alternating circuits, let's say, alternating class. So what is an alternating class? So this is basically uh, so these are all circuit classes, where circuit families, where you have every layer, like every so your circuit, we're going to think of now as a layered graph, that and for example, this is the output gate and it belongs to a specific layer, and at the bottom the input gates x1, they belong to one layer, and every layer after that is an alternation. Okay, maybe here you also have x1 bar to xn bar, the negated variables, and every layer is going to be so for example, let's assume that the bottommost layer is just above the input is an and, then the layer above this has to be an or. Yeah. And so on, and then now after this it's going to be an and let's say and this is an or. So this is an alternating class, and so what I allow is I allow unbounded Fanon for the uh, gates, which means the Fanon can grow as a function of n, right? And similarly, I also allow, I mean, if I don't mention it in a circuit, the fan out is always unbounded. Okay, and it can be reused multiple times. Yeah, and okay, so I'm going to parameterize these classes by this letter I, and what I mean by this letter I is that the depth of the circuit is going to be restricted. In the longest leaf to root path for a circuit in this ACI class is order log raised to I n. Yeah, which is the same as just log n raised to I. Okay, so why? So right. So is this? I hope this definition is clear. Yeah. So unbounded. So basically, this class maybe I erase this is characterized by unbounded Fanon gates over yeah, and
As well as unbounded fan out, unbounded fan in as well
yes,
as.
yes, fan in, fan out. If I don't, yeah, fan in, fan out, yeah, fan out gates, and the depth is going to be order log to the. And for other measure, I mean, also whenever all the circuit families I'm going to talk about mostly are the size is always poly in it, polynomial in it. Yeah. So n to the order one for a fixed constant. Yeah. Okay, good. So so let's look at so what is AC0? So well, AC0 for us is going to be poly size constant depth right? And unbounded Fanon circuits.
Can you explain
Yeah.
why this log power I is a natural way to parameterize this class?
Right. So see, the thing is, so I already mentioned that circuit complexity is like about like somehow trying to capture this notion of parallelizability. And in particular, so what do you mean here is like, okay, so you have a problem. If you have a problem which is, can be was an algorithm which can be implemented in ACI, right? So essentially, you can think of each of these gates, right, as a separate processor. Right?
Uh-huh.
For example, you can think of this as maybe you have, so so if I have one gate here, if I have unbounded fan-in, so and the whole size is, if let's say the whole size of the circuit, if it's n to the order one, then every layer could potentially have n to the order one many gates, right? So you can think of somehow as when you have an algorithm of this form, you can allocate the computation of in one particular layer, each gate to a separate processor. So for example, I'll give so somehow this captures this parallel random access machine model. So you can think of this as okay, this will be done by processor one, processor two, processor three, and so on. Right, processor three and maybe processor k, where k is some polynomial. And after doing this whole computation, this process again get reassigned. Now they're going to work on this other layer of doing this OR and so on. So in some sense, this depth in this circuit class captures the parallel running time. The depth captures parallel running time, uh, uh, parallel time complexity, for example, of your problem, right? And the size captures sort of the number of processors. So as a result, if a general poly-size circuit is somehow capturing a polynomial time computation, because it could be, it's just saying that, okay, there are polynomially many operations that you finally do, right? If you go to this poly-size circuit that we have here, so in general, so this depth, if the whole size is poly in n, then this whole depth also could be like poly in n. So it's sort of like a very sequential computation. And the number of, if you can layer the circuit and look at the number of gates in a particular layer, essentially that is capturing how parallel
Yeah.
you can make your computation, right? And in some sense, when you have log to the I, that is sort of like as compared to, uh, I mean, so that's like your notion of fast parallel time, right? Like fast parallel computation, sort of, right? I mean, like, yeah, it doesn't make sense. I mean, um, so so why? So your question was why log?
Why log power I? Like, I mean, it's not that I have an alternative parameter to suggest, but like I have a circuit of size n. I mean,
Right,
there are in n input variables,
right.
and then like in log n, I don't know why it will make sense to.
So let's okay. So why it makes sense to, so why not see? Mm, I mean, you could also pick something something like sublinear, like less than. So you could pick something like um, uh,
Yeah,
well,
maybe
you could
there is.
do.
Yeah, maybe log n. Yeah, log n makes sense. Yeah, because it's like it's
It's
like
some sort of an
not
exponential speed of given parallelism, right? I mean,
yeah, yeah. So
you're
log
sort
n
of,
is like you are not making use of any yeah, it's just like a tree.
yes. It's just like a tree. So yeah, you need at least
Shortest circuit which can see the entire input.
right. So let's define this other class, and then I think like this login probably makes more sense there,
Yeah.
right? So this other class, which is called NCI, and which is very arbitrarily named. This is actually, it's called Nix class for
Yeah.
this.
And I also had another question about this
Yeah.
class,
Yes.
which
Yes.
is that so we know that when you have a Boolean function, it can be just either CNF or DNF. You just need one alternation for any
Yes.
Boolean function. Yeah.
Yes.
But here we are saying that we are restricting the size to be polynomial. So that
Yeah.
so not every Boolean function can be written in polynomial size using just one
Yes.
alternation. But do we have? I mean, can you give me a function which is not possible in two alternations poly size, but like it is possible with much higher alternation poly size. Is there any easy example to see?
Yeah, we'll look at a couple of examples. So one example, I mean, so easy example as in like,
It's obvious to see,
yeah, I mean, like, for example, parity, for example, is a very easy example.
Uh-huh.
In the sense that, but here, the number of alternations you allow has to be non-constant. I mean, for example, if you,
But
I
it is
mean,
not clear that it can be done in constant depth, no?
it cannot be actually. In fact, it cannot be done in constant depth and polynomial size,
Yeah.
but you can do it in slightly non-constant depth, like log n by log n. I mean, like, okay, log n, it's easy. So,
No. But I'm asking that it cannot be done in constant depth is not easy to prove, or
yes, it's not easy to prove. I mean, it's like it requires like I mean, it requires at least one whole lecture, like I would think.
okay.
Yeah, but the fact that it cannot be done with two is easy to. I mean, the fact that it requires exponential size for CNF and DNF, that is easy to see. Um, yeah, in general, if you want a problem which can be done easily in, let's say,
But
by
even with unbounded fanning,
yes,
parity is not computable. Yeah.
yes, even with unbounded fan and parity is not computable in constant depth, in constant depth and polynomial size. So we'll see this like very soon.
Okay.
So let's look at this NCI, and this NCI is defined similar to this ACI, except that yeah. So it's the same. The depth is again order log to the in. Size is again poly n. The only difference here is now I'm going to restrict the fan out, fan in. Sorry, the fan in is going to be 2. Okay, the fan in of every gate is going to be 2, or at least you can also go with constant. It doesn't matter, but without Joseph generality, we can always make it 2. So the fan in of any gate is going to be 2. Okay. So what is the right? So one second. So all right. So let's look at how this would restrict this. Let's look at this class NC0. Right. So what is this? This is going to be constant depth,
Bounded fanning, constant fanning,
bounded fan-in. Yes, exactly. Bounded
poly
fan-in
poly
and poly size. But yeah, here's the question. So what is poly size? So is it even possible? So let's see. So what we have is some sort of uh, constant this thing, right? And I'm saying there's only let's say some constant k depth.
Yeah.
But in this case, if I started out with a gate like this, it can at most reach 2 to the k leaves,
Yeah.
right?
Mhm.
And if k was constant, then this it cannot even read the whole input,
Yeah.
right? So NC0 circuits cannot even read whole input. Read the whole input, but they are very useful actually. We'll see some actually a use in today itself. Uh, so clearly there are it is easy to come up with functions that cannot be computed by them. That cannot be computed by, right? Any function that depends on more than constantly many bits, that cannot be computed by a
Yeah.
NC0 circuit. Okay, and the second, but the more interesting class, and this is the only, hopefully the only class we'll talk about in this course, is NC1, and that is basically order log n depth. Circuits of constant fan-in and polycells. Okay. So, okay. So one small exercise that I'll just leave as this thing is for circuits, both, and this is both for NC1 and AC0 and even NC0. You can, without loss of generality, assume fan out equals 1. Right? You can make the fan out 1. You can, in fact, like the DAG can actually become a tree, and you will still compute the same function, but maybe you will incur a polynomial go. Okay. It's a rather simple, a very simple way to do this, like is to just duplicate. If you have a gate like this, and if it, let's say, it went into multiple, if it was, so the fan out is high, so basically it went into multiple gates, then what you would do is like completely create copies of subcircuits, use a separate copy for each of these gates, each of the, if these are G1 to GK, and they all, if they all fed by the subcircuit C, then you create new copies of the subcircuit C that which is entirely to be used by independently by just G1, by D2, and so on. And this will not blow up the size by more than a polynomial factor. Okay.
If the depth is constant, then I agree.
Mm.
But if the depth is, let's say, log n,
Yes, but yeah.
then it could I mean, because you have to create copies inside copies now.
Yes, but right, but the thing is, like in this NC1 setting, you can always do this. So 1 second. So let me just think. So I'm just wondering if in NC1, by definition, you should also probably assume, I think fan out is 2. Is also constant, actually. Yeah, you're right.
Mhm. Okay.
Yeah, sorry about that. Yeah. Otherwise, like as you pointed out, it could blow up into a super. I mean, something which is non slightly, which can grow faster than a polynomial. Yeah. Uh, yeah, I was wondering whether you can somehow recover this. But anyway, for the definition of NC circuits I've given, maybe if we'll just, it suffices to assume fan in and fan out as constant. Um, but maybe if somehow if fan in is constant, probably you can make fan out also constant. I'm not sure, but anyway. All right. So we saw that you can easily come up with examples where which cannot be computed by NC0 circuits. So the first interesting family of circuits for us is going to be AC0. This class AC0, right? Already, like we saw, I mean, we've seen the simplest example of AC0 circuit is probably just like, an unbounded OR gate and unbounded AND gate. This is like uh, uh, depth 1 AC0 circuit. If you are more, I mean, AC0 itself is constant depth circuit families, but if you're even more parameterized your circuit by depth, the exact constant, then and CNFs and DNFs are exactly depth 2 AC0 circuit, right? Because one starting with so DNF, which is an OR of ANDs, and CNF, which is and a force. Okay. So there are, so we'll see later that there are functions which they cannot compute, but they can compute a lot of interesting functions. Okay. And in particular, since you're going towards, so if you recall, our goal is to somehow show that majority has some sort of, to understand the space complexity of majority. And the way we're going to do that is we're going to study majority, the circuit complexity of majority, and then relate circuit complexity to branching program complexity. Okay. So in particular, let's start with some functions which can be computed in AC0. Okay, but okay, before I go there, maybe I'll just leave as an exercise this following simple containment of complexity classes, which is AC. So, okay, so by definition, NC0 is contained in AC0, right? Because it has bounded fun and constant depth, and here you have unbounded fun. But also this AC0 can be contained in NC1. Right? And so why is this the case? Yeah, so I leave this as an exercise. It's not a, it's a very simple, I mean, composing two things that I already mentioned. You first convert this AC0 into a tree, and then you sort of build for every AND gate and OR gate, you build a log-in-ary tree, sort of. To you can work out the details. It's pretty simple. So let's look at a couple of so what is the majority function, right? I mean, how does majority function look like? The majority looks like, so to decide majority on an, if I give an X and then the binary string, n-bit binary string, and if I wanted to somehow compute majority function, so what I have to do is I have to look at the string, count the number of ones in X, right? And compare with n by 2, right? And see if it's greater than n by 2, then you output an 1, otherwise you output a 0. So this is exactly the majority function. So now we'll come to the counting part eventually. So can we, if somebody gave you a count, can you check whether, can you compare two numbers basically? Because n by 2 is again some number in binary. So a simple way to abstract out this problem is, one part of this problem is this greater than equal to function. Greater than equal to of x comma y, well, what is it? It's 1 if and only if, as binary numbers, right? I mean, basically, xi to the I is strictly greater than yi to the I, right? And so this function I claim has a constant depth implementation, right? So why is that? So, well, so you know that this is true just by analyzing as a bit string. You can write down a formula, right? You can probably write down a logical formula for this. So there exists. So how do we write it? So there exists some I belonging to n. So let's say these are n-bit strings, right? Such
So
that,
you just
yeah,
you just said that there is the most significant bit
yeah,
in so there is the bit position I, so is that towards the
right,
left of I, both xi and yi are 0,
right,
and in xi it is 1.
exactly.
Yeah.
Right. Basically, there should be some position where xi is a 1 and yi is a 0. And before that, maybe they all agree, right?
Yeah.
So this is exactly phrased as such that xi equals 1 and yi equals 0. And for all j less than I, uh, either xi equals 1, sorry, xi equals 1 and yi equals 1, or xi equals 0, and basically they completely agree. Sorry, xj should be j.
So which is your most significant bit? N?
Xn. Yeah, n is my most significant bit, let's say.
Then it should be j greater than I.
Oh, sorry. Yes. Right. Indeed.
And it should be like xj should be, you don't need xj equal to 1, yj equal to 1.
Right.
Yeah. No.
I mean, yeah, no, you need that. Yeah.
You're right. You need
I mean, just covering both the grounds. Right?
Yeah.
And this actually has a nice circuit implementation because there exists I quantified over n. I can just I can have an OR gate of fan in n, and the remaining thing, and then there's a right, and then you have an and you have one more and of over for all j greater than I. You have this. Right, so it's a simple, I mean, you can just convince yourself that this is like a constant depth, maybe depth 2, depth 3 implementation, but some constant depth. Right, and it's polynomial size, poly in n size. It's simple implementation. So now let's so slowly let's move on towards so okay, well, like last time I'll stop at maybe that the 1 hour mark and uh, maybe give like 10-minute break and then I can continue.
Yeah.
Okay, so now what is it? So okay, so let's look at the next most simple thing. If you want to do counting first, a simpler operation that you want to do is addition, right? You're given like two binary strings x and y, and maybe okay, and you want to find this string which is uh, the sum of these two. But if I wanted to phrase this as a decision problem, I want to say addition is basically set of all x, y, I, where or whatever the ith bit of x, y, I is 1, right? The ith bit of x plus y is 1. Yeah, so essentially if you can produce, is it possible to compute the ith bit of x plus y? So let's if you remember, I mean, the standard way we do this is this carry, I mean, triple carry or whatever, this adder, right? I mean, if let's say, for example, if you wanted to add these two, so you will maybe add 1 here. So you generate 1 plus 1 is 0. So you generate a carry here, then again you generate another carry here, then go here and generate another carry, and here it's going to be 1. So this is this is the sum of these two numbers. But this is inherently sequential, right? I mean, you generate a carry, you ripple it, and if I actually, so let's just try to write down the formula for this, like what is the Boolean circuit for this. So what you would do is you will say, okay, the z0 is the sum of x and y. Let's say z is the sum of x and y, and z0 is basically, you know, x0 parity y0, right? And you generate a carry, then the c0 carry is basically, you generate a carry if both these are 1, so that is just x0 and y0, right? And in general, the ith bit is, again, you're just doing an XOR, so it's xi parity yi, and then parity the carry from the previous one, that's ci minus 1. Okay? And the carry at the generated at the ith position is essentially nothing but, well, when it is generated, either it's generated when I mean, of course, when the bits themselves are 1, so xi and yi, or it could be generated by so this following, so xi or yi. So basically one of them is 0, then there is no carry generated here, but somehow you have to add it with the carry from the previous one. You still have to account for the carry from the previous position. Yeah, so is this clear? So these are the sum and carry bits, like this is the standard ripple carry method, right? But of course, you can exercise. You can check uh, uh, check that the depth is. I mean, it's as large as the number of bits you're producing. So it's order n. Right?
That is because you have these alternations coming in. Yeah. And then
Yes, yes, yes. And also, yeah, and basically, yeah, you're plugging in ci minus one. You're plugging in this, right?
yeah.
So yeah, I mean, ci
But
is recursive.
but if we were just plugging in an AND formula inside an AND formula, we could have
Ah,
done that in AC0. Yeah.
yes, 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 exactly, exactly. If you had something where you had only an and formula, then you could have just collapsed the whole thing and yeah, you could have done it. But yeah, but there are ors in the middle, and so there is some alternation here. Right. So this is actually a depth two circuit. Depth two circuit, and but then of course depth two circuit in terms of the ci minus one, given that ci minus one is a as a variable, right? I mean, but if you also have to compute ci minus one, you keep nesting this and you will incur order n depth.
But this is not a formal proof. Yeah, that we can't do it in.
No, no, no. Yeah, yeah, yeah. No, no. But you can do addition in constant depth. That's the so that's the cool part.
Okay, okay, okay.
Addition actually you can do in addition actually belongs to AC0. So let's see how. And this is actually it's called I mean this digital design. You might have seen this carry look ahead adder. Uh, so what is the idea here? Well, the idea is somehow you want to. So when does this carry occur, right? I mean, when a carry occurs, so let's say for example, uh, uh, so let's no, so yeah. So let's say you have you're summing up two numbers. Let's say an to a1, bn to b1, maybe a0. Right. Uh, Now, so when I do A0 and B0, so there is a carry in C1 is so C1 is 1 if and only if A0 equals B0 equals 1. Otherwise, there's no carry, right? Both A0 and B0 have to be 1 for me to get a carry in the first place here. And in general, if there is a carry, let's say CK, and if a carry has to occur here, either it's produced in the previous thing or it's produced somewhere behind and it's sort of like rippled through into this position. Okay. So for CK to be 1, right, a carry bit has to be generated. A carry bit has to be generated at some position I strictly less than k, and yeah, and should be propagated all the way to this place, propagated to k, right, to position k. Right. So let's try to write again, like last time, let's try to write a logical formula for this, right? For this fact, for this particular thing. So how do I write this? Like, well, the way I would write it is CK equals, well, there exists I. This is one if there exists I uh, uh, between, okay, so there exists I. Um, um, 0 less than equal to I strictly less than k, right? And what should happen? Either AI and BI. So basically, a carry is generated at some ith location somewhere, and right, and for all j, right, where 1 is strictly less than j is strictly less than k, aj or bj. I mean, it cannot be that both of them is 0. If both
No, no, no. I don't know what happened. I restarted it. Yeah.
oh, I see, I see. Okay, okay, sounds good. So let me just, yeah, I'll finish this. Actually, we are in good time. So in another 5 minutes, I'll just finish
Yeah,
it.
but I have a doubt. It should be
Yeah.
for all j,
Hmm.
that j has to be uh, s- smaller than I.
Hmm.
Yeah.
Uh,
No, it has to be between. So I is the,
oh, sorry. Sorry, no, it's not one. This is I. Yeah.
yeah,
This
yeah,
J between I and K. Sorry.
yeah,
Yeah.
yeah, yeah.
It's not one. Yeah. Sorry for the typo. Yeah. So this J has to be between I and K, right? And you have to make sure that, I mean, and this formula should be satisfied. Like, I mean, basically there shouldn't be uh, a zero. If this is zero, then we are screwed. So we shouldn't do that, right? So I mean, if this is zero, basically then the carry will not propagate after it, right? So right, and again, like this has a very nice this is a constant depth implementation, right? Basically you have ck, so this is a circuit. You basically put an or, and this or this has
Yeah.
whatever from zero.
So here, one thing is that the carry might originate much farther. Yeah. But
Yes, yes,
we are just checking that from I onwards, also one carry is coming.
yes.
Like
Yeah,
if yeah, yeah.
I mean, so yeah, it's so basically you have to you have to make sure, you have to just know whether at that particular place this thing is generated. I
Okay.
mean, there is a carry present, that
Okay.
ck for that bit is present, and for that it can either come like this or this way, one of them.
Yeah.
But once it's generated, you just keep it and you are going to the next one, right? I mean,
Okay. Okay.
it's and this is so that's it. Again, this is like this implementation is a order one depth implementation. And this shows that addition is an AC0, right? So there's a constant depth. So in fact, this also means that addition belongs to NC1. And
One
that's
second.
how,
One
ah,
second. So this CK,
right.
what is the circuit like? It has to be. It cannot be like. Uh, I mean, there are like, it is like some depth for or something like that.
Yeah, right. So I mean, so here, for example, if you write it for all I equals k, so then you're checking. Uh, Here you're checking one small and check. You're doing AI and BI, right? And then also what you're doing is an and, big and here, and this big and is over this j, right? I mean this j, uh, so this and over j, right? Okay, so actually you have to, this has to depend on I, so this and cannot come here, so this and has to somehow come down here for every I. So this is a quantification of I, and this and circuitry actually will come here. Uh, right, and for all j, and here another or, you'll have AJPG, right? Is this clear? So just so the nesting is a little, so because this j, the range is between I and k, right? So maybe this is 1 2, sorry, starting with 0 1 up to k, and here right, yeah. Yeah, so here this is going to be this j, this thing is going to be between I and k. So for example, if it is 0, then it's like goes from 0 to k. The circuit here, uh, AI BI, and then here this j is now going to go from 1 to k, right? And so on. But it's nevertheless a constant like for depth 3 or depth 4. All right, so I think it's a good time to stop. When we come back, let's finish up why majority is in NC1 and let's move ahead. Okay. Can I stop? Let me stop. Any questions? So was this clear, Aman? Was it fine? Okay, so that shows that addition. So in fact, so we saw that addition is in fact you can do this in constant depth. Um, as it turns out, okay, so constant depth circuits are quite powerful. They can do addition, but somehow it is known that there are many things which they cannot do. In particular, so there's this very famous result uh, due to a large number of authors, Sachs-Sipser, first Sachs-Sipser, in all in the 80s, maybe I won't say. I think Yao with like uh, and also I guess Rasborough. It says that the parity function on n bits, parity n, requires depth d AC0 circuits of size 2 to the n to the 1 over d. Okay. So this is a low bound result, very famous result, and so it came out in the 80s. So essentially, you know that, and what do we know? We know actually this upper bound is tight. There are AC zeros depth d. So let me denote the subscript d. Let me denote the A0 depth d fragment. Circuits of 2 to the n to the 1 over d size computing parity. And this is what is called a non-uniform lower bound. So usually, so when I introduce this model, non-uniform model of computation like circuits, usually they were sort of like studied in the context of lower bounds, because the model is much more powerful. So when you prove a lower bound against such a model like that, it's like a very strong result compared to like what you might prove against like an algorithm. This is like saying, however you allow how much of power you allow to the algorithm designer, there are some very hard problems, right? So okay, so this is and in fact the same low bound also holds for majority. Also holds for majority, right? Okay, good. So let's but it's very easy. So at least, but it's easily seen that these two functions are actually in NC1. Okay, so let's first see. I mean, it's probably very easy, simple to see why parity is in NC1. Parity n belongs to NC1. So why is that? Well, so if I had a n-bit string x1, x2 to xn, then what I could do is, by using this associativity of parity, I can do some sort of divide and conquer, right? So I can do a parity. So by this O plus, like whatever, this plus, I mean this parity here. And then, and so on. I keep doing this. Like every time, so here there are like n bits I had to do a parity of. Here it will be n by 2, and so on. And in general, in log n steps, I'll be done. Right? Right. And this depth is log n. Okay. And uh, And what about this function? This is actually computable in NC0, right? It's a NC0 computable function because it's a very it just depends on 2 bits, and there's an easy circuit for a 2-bit parity function, which you all know, right? Just by definition, and you just plug in that NC0 circuit, then you actually stay within NC1, right? So basically, so here's a small result which might be interesting, so on. So if I had NC0 circuits like this, and if I made a tree out of such NC0 circuits of log n depth, that is, you still order log n depth, this is still belongs to NC1.
Yeah.
Right? And that's the same reason why parity is in NC1. So here's a function which can be computed in NC1 but not in AC0. So let's go to so we saw integer addition first. Let's look at integer multiplication because this is more of a more interesting. So because it's like sort of multiplication anyway, we define often as repeated addition, right? So if we can do addition, can we do multiplication in constant depth, right? Or at least in NC1, right? Because the naive method doesn't give you an NC1 directly. So first, let's see what is the simplest thing we can do. So let's just do an example. So let's say you want to multiply 1001 times 1101, right? The way you do it is like, how do you do it? Like you just like shift and write. So you'll write 1001. So yeah, I mean you can do it either way, but 1001, and then maybe the next one is a 0, so it's all zeros. So and 1001, and then again 10. Right. When I multiply in general, two n-bit numbers, the sum and this finally you sum it up, right? Sum of the you sum of this, you sum of this, you sum of this. So in general, integer multiplication reduces to somehow some iterated reduces to iterated addition, right? And iterated addition is somewhat like majority, right? Because that's exactly what. So okay, so good. So what is the complexity of this, right? So one way to do this is like I can simply do if I had if I am multiplying two x1 times then in general I'm going to have how many so basically n shifted rows, right? So or rather, yeah, n plus 1 rows, and the number of columns is going to be something like up to 2n, right? So one thing I can do is that if I can somehow add these two numbers together using the addition algorithm that I already had, right, which can be implemented in constant depth, and which is indeed also in NC1, then I can build a tree out of it, right? An addition tree. So I build these two, I add these two. Maybe I'll write it this way. I'll add these two, and then again add these two, right? So when I say add, this is the previous algorithm that I had. Let me write A. Yeah. And then again I can add these two, just make a tree out of it, and this tree will be log n depth, because I mean you start out with n plus 1 rows, right? You're adding two rows together, two rows together, two rows together. So in log n steps you will be done, right? And what do we know? Each of those A's, they can be implemented in constant depth, but they have unbounded Fanon,
Yeah.
right? So, but I can make it bounded Fanon and log depth, right? So I can replace each of this A belongs to NC1, right? So what we have now is like a tree where everything is an NC1, right? And this is actually this is going to be not, this will not be NC1, right? Because uh, uh, the whole depth, the total depth here, because each of those things itself is order log n depth because it's an NC1. So this whole thing is going to be order log squared n depth, right? And this is actually, it's NC2. So what we just did, this shows that whatever integer mult, this belongs to NC2, okay, log square depth, and which is not very nice. So let's, and in fact we can do multiplication in NC1, and that's a very nice trick, and this will also give us our majority algorithm. So let's go ahead and do that, like see how it is. And this trick actually, it's called a 3 to 2 trick. So what is the idea behind this? So what did we see? So we had this bunch of uh, these staggered rows that we are adding, right? Now the idea behind the 3 to 2 trick is as follows. So you have so here's a claim. Maybe I'll write it as a formal statement. Claim. Given A, B, C belonging to, which are the n-bit numbers, right? There exists D and E, and maybe these are n plus 2 bit, let's say, right? Such that A plus B plus C equals D plus E. Okay, so somehow every three, I mean, like you have, let's say you have 3 numbers, so you're sort of like reducing sum of 3 numbers, you're reducing it to a sum of 2 numbers, right? Firstly, notice that if you do this, then you're done. Like if so if let's say, let's assume this, assume claim, assuming this claim.
But I don't understand. You
Hmm.
just take D to be A plus B. I mean, what is the, I don't understand what is the claim.
Oh, so I'm saying like, okay, so and you can produce this in NC0. Sorry, sorry, it's a good
Okay.
point. Yeah, you can produce D and E in NC0. Yeah, thanks. Sorry about that. Yeah, so sorry, missed out on the. Is that clear? So you can of course produce this like you correctly pointed out. You can just use take A plus B to be D and C to be E. This but then to produce D, you will have you need an NC1 circuit, right? You can do it in constant depth AC0 circuit, which is an NC1. But here we are saying that we can do it in fact in NC0 with using extremely local operations. Okay, so okay, maybe let's see the proof of this. Why should this hold? And this is exactly, it's going to come from the carry look ahead trick that we saw. The carry look ahead adder that we did, right? So in fact, what is going to be D? D is going to be something where I'm going to define DI to be just AI parity, BI parity, CI. So remember, you have, so what is happening? So you have AN to A1, and then Bn to B1, and then you have Cn to C1, right? And all we are going to say is, so yeah, so you want to add this up, and now we want to produce 2 things. So what we can do is, like, I mean, of course, you can just use the same carry trick. Now all we have to do is produce 2 numbers, one of it which is just the, like, the parity of these things, the other thing which gives the carry. Okay,
Okay.
right? I mean, then I've just produced 2 things which are the carry, but I have to produce a carry as a number, not as like a bit by bit, right? So here's what I claim, here's what will work. So
But
what I'm going to,
carry is not in NC0. No, we have said that carry is in, can be done in AC0 or NC.
yes, sorry, no, carry actually was
AC0 as well as NC1.
yes. So one second, so where is it? Yes, so this is what we produced. Yeah, so but this is not going to be carry in the sense of exactly the carry. So let me just 1 second. Wait, my screen is this thing is freezing. Just give me a minute. Okay, good. So, all right. So, okay. So, in fact, let me do this with an first. Let me do this with a small example. So, what I'm going to do is I'm going to do, let's say 10101. So that my ABC are going to be 10101, 011, 00, okay, 111, 11, all ones. Okay. Now I claim that if I take di to be this and ei plus 1 to be the majority of ai, bi, and ci, then I'm done. Yeah, and I take e0 to be 0. Okay. So notice that even though in the previous part, what I actually did was we actually produced this whole carry look ahead, right? We looked ahead at the carry and so on. So here what we are doing is we are just reducing the addition of 3 numbers to 2 numbers, right? This is sort of like a slightly simpler problem than actually adding and producing the output of 2 numbers, right? Here we are not adding and producing the output of 2. We're just giving 2 numbers which are going to sum up to the same as the 3 numbers that you initially had, right? So in this case, like for example, let's look at this example. So what will be the parity of this? So the parity string is going to be, okay, firstly, let's work out this example completely. So the addition is going to be here, it's going to be 0, and then you will generate a carry. And then again, you'll generate a 0, and then again a carry. But now you're going to generate 1111, so which is like 1 plus 1 is 10, 10 plus 1 is 11, 11 plus 1 is, so you're going to generate 100, like you have 0 here, you have 1 0 here.
Yeah.
And similarly here, what is it? So 10 plus 1 is 11, 11 plus 1 is again 100.
Yeah, 10.
Right, and then again another 10.
Yeah.
And here again the same thing. So now you put 100.
Yeah.
This is your addition, right? So
Yeah.
let's look at the this method, the whatever. So let's look at the parity first. Let's look at the parity of all this DIs. So the DIs is going to be, what is the least significant bit? It's going to be 0. And then it's going to be, so least significant bit is the parity of this, and that's going to be 0. And then the next one is 1, and the next one is again 1, and the next one is 0,
0.
and 0. Right. So this is the, and let's look at the majority string that you're going to produce. The E0 firstly is going to be 0, right? And the E1 is going to be majority, and the majority here is
0.
no, the majority of the last one, the last
Okay, last. Okay, yeah, that's 1.
That's 1, and the next one is 0, and the next one is 1,
1.
and then 1 and
1.
1, right? So let's look at the sum of these two. With these two numbers, if we sum up, we should get the same thing, right? So 0, 0, 1, 0, 1, 0, 1, 0, 1, and then this step. Same thing, right? So it is so what is the idea here? Like basically, we are reducing the sum of 2 numbers to they're reducing the sum of 3 numbers to the sum of 2 numbers, right? So essentially what we are doing is like so we are trying to get so this new number that we are producing is exactly the carry string, right? I mean the carry string, which if you added with the parity of these 3, you should get the final number, right? So is this?
I still don't understand. I mean, it looks like magic. Why? I mean,
So see, basically the second string, so the second string that we produce is just the set of carries produced, shifted by 1 bit, right?
yeah, that is true. That is true.
Right. That is all this new string that you're producing is just the set of carries, but just shifted by 1 bit.
Yeah, but as we saw that in the
Hmm.
case of three numbers, the
Yeah.
carry could be like more than one.
Yes.
Like it could be 1 0.
In Yes, yes, yes. It can be 1 0, but can never be more than 1 0. I mean, it cannot be more than 100, right? I mean, it cannot. It can only be.
So yeah, so majority I agree that it is just indicating that there is a carry produced, but it
Yes.
is still not. It's not representing the true carry. It's not saying whether the carry is 1 or 1 0.
Yes, 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 yes. So yes, it's not representing. See, okay, so the correctness can be just argued by the by a simple case analysis. So I thought I'd leave this in access, but like you just see that, I mean, if the string had like all three zeros, right, then of course your choice of E0 equals 0 is correct, right? Because I mean, the first bit is, it's not going to. So what happens when so 1 second. So um, see, yeah. So basically, so the proof of is just like, I mean, it's a simple, it's a proof by construction. So basically, you can just so if you had an odd number of ones here, if the parity of the sequence was 1, right, then what happens is that is already reflected in the corresponding di that you produced, right? So essentially, so you have nothing to worry about. But if you're if and right, so and now uh, okay, so 1 second, so let me just think, why would hmm, I see, yeah, so 1 second, so yeah, I see, yeah, you can prove this just by induction on n. But otherwise, I mean, yeah. So it's not. There's nothing deep to the proof. Yeah, it is indeed like it's a very magical proof. I don't have much by way of intuition about this proof, except that it will work. It works.
All right, all right.
Okay. So yeah, I wanted to leave this as an exercise. Like, it's just prove this by induction on n. You can just prove this thing, and the main thing you're going to use is that basically that I mean, just simple case analysis where you say that, okay, what happens when this parity is because you're only summing up, you're reducing three numbers to two numbers, right? There are only some finite settings, and you can just look at it and make sure that it works. There is also another couple of very interesting ways to show that majority is in NC1, but unfortunately, again, these are like sort of like the way I would say it is like it's I mean, the idea is very natural, but the proof of correctness is quite hard. So let's say you had a okay, firstly, okay, this is not firstly, I'm doing this for integer multiplication, and for integer multiplication to show it's an NC1 without using this 3-2 trick, you can do this, but you have to use some heavy number theory machinery. So for example, in particular, you have to use this Chinese remainder theorem. It's a fairly natural idea if you think about um, uh, it, how why this should work. Um, but yeah, but I'll not go through this. The other idea is okay. So
What do you need Chinese reminding for?
so you can essentially, if you had, let's say you want to produce x multiplied with y.
Uh-huh.
Right. So then what you can do is, if you knew x and y mod a set of primes,
Uh-huh.
p1 to pk,
Yeah.
right? Then what you can do is you can reconstruct, you can take, so xy, what you can do is you can do the multiplication in the Chinese remainder basis, and then you can reconstruct it.
Uh-huh.
So actually this idea is it's sort of, this is the idea which gives the most efficient circuits for integer multiplication, the Chinese remaining idea.
Uh-huh.
Because one thing that I didn't really yeah, so because uh, it sort of like gives you in one shot integer multiplication and also integer division.
Uh-huh.
So both these things you can do using Chinese geometry. And in fact, this idea will also give you iterated uh, uh, integer multiplication, where you're not just multiplying two numbers, but you can multiply n numbers, n bit numbers in NC1. Okay, so or like divide. So this is x by y. This is like x1 times x2, x1 multiplied by x2 multiplied by xn, where all these are n bit numbers. Both these things we can do this provided by using Chinese remainder. But maybe I'll mention a bit in the next class, because it has very close connections to, I mean, all these circuits that we're talking about. It's very important to talk about this notion of uniformity for the circuits, because otherwise these algorithms are not very useful. Uh, you need very simple or very local descriptions of the circuits for doing these operations. But regardless of that, like in our case, like just notice that we are looking only for majority. And to do majority, we already saw
But,
how to.
yeah, but did we finish this proof of addition doable in NC? I mean, multiplication doable? No.
So right, sorry, yeah, okay, right, great point. Yeah, thanks. Yeah, so let me just finish that proof.
Yeah.
So let's assuming this claim, I claim that we are done. Like if you can reduce A, B, C, three numbers to this two, right? So then what you have here is uh, so you know that anyway multiplication is just iterated addition, just
Yeah.
shifted iterated addition. So what will you do? So you have, let's say, so you have basically each of those rows, let me call them R1, R2 up to Rn plus 1, the n plus 1 rows. Now what you will do is you will add reduce this in NC0. The important part is NC0. So basically these things are all local, right? Because this majority function on 3 bits, as well as
It could
this
be
parity
R2N, no? R2N.
uh, R2n. I mean, so basically, if you had two,
If you're multiplying two n-bit numbers, then there
right?
are like 2n shifted numbers, and then you have to add each of them pairwise. Yeah.
Yes, you're right. Yes. Sorry. Yeah, it's right. 2n shifted number, so it's like R2n. Yeah. Uh, and so now what you can do is, I mean, so now basically you divide this into, so you started with 2n numbers, and what you produce here is actually, you reduced, you grouped this into numbers of 3 each, and you add, right? And then in the first level you produce 2n divided by 3 numbers, right? So right,
2n divided by 3.
actually
2 by
4n
3.
divided.
Yeah. Yeah. 2n into 2 by 3.
Yes, 4n by 3 numbers.
Yeah.
And you keep doing this, right? And you keep doing this. The next time, I think you will get 8n divided by 9, and so on. But the main idea is every time you're cutting down by a constant fraction, right? And in the end, you will be left with maybe just a constant two numbers, maybe, right? In the end, I claim you will be left with two numbers. And this whole thing, the depth of this recursion is basically log
n to the
log
base 2 by 3.
2 by 3. Sorry, 3 by 2 maybe.
3 by, yeah.
Right.
Yeah.
And yeah, so yeah, so yeah, this is, and every such reduction is an NC0 circuit, right? So you in NC0 you produce this thing. So the overall circuit is going to look something like, I mean, like our old setting, it's going to be, you started with these n-bit numbers, or 2n n-bit numbers, and in NC0 you finally reduced it to here you reduced it to 2 n-bit number, 2 not n, is it n-bit? Maybe not n-bit, but maybe n log n-bit numbers.
I just missed what you just said in the end. What
So because like every time so if you look at this numbers, this D and E that you produce,
yeah,
they will be like n plus 2.
yes.
So they will slightly grow in length, but not too much. They will at most grow up to n log n factor added to the length.
Mhm, mhm.
Why is that? Because
There are
every
only
time
that many levels. Yeah.
yes, that many levels, and every time you're only adding constantly many bits.
Yeah.
Right. So finally, you reduce it to addition of 2 n log n bit numbers.
Yeah.
And addition of 2 n log n bit numbers. This is an NC1. Right, because it's just I mean, addition of 2 n-bit numbers is an NC1, and n log n is, it's only a polynomial factor away, so it's not, it's just slightly a quasi, right? So here I'll put that addition circuit for this this addition circuit. I'll put it here. So the overall depth is, this is log n, and this
But
yeah.
the height, that will be log of n log n, no? It will be log n plus log n. Yeah.
Yes. Okay. Yeah. If you are, yeah. In
But
fact,
it
you
is
can
still
make,
log of log n. Yeah.
yes, the n log n you can consider it as n squared.
Yeah.
So if you take two n squared bit numbers, still you can do it in order log n squared, which is just order log n.
Yeah.
So this whole thing, so this shows that
So who invented this 3 by 2 trick?
so it's called, I mean, I checked, I think I didn't, so it's always I read somewhere that it's called by somebody called Hoffman. It's called Hoffman's trick. I don't know who this person is.
Mhm.
I don't even, yeah. Yeah, so it's sort of folklore, nobody mentions it, but somewhere I read that this is called, somewhere I saw it mentioned that this is called this Hoffman's trick. Okay, so okay, so this shows that integer multiplication is in NC1, and but it also shows that because we did iterated and also iterated addition of is in NC1. Iterated addition of n-bit numbers, which is I mean, which is naively how integer multiplication reduces to iterated addition. This is also an answer, but majority is nothing but at least the counting part of majority is nothing but iterated addition of 1-bit numbers. Right, because you're given,
You are only taking care of checking
yeah,
if the first bit or so. Yeah. No.
no, so you're given n bits, and then you want to sum up all the bits and check whether this is greater than, maybe let's say,
Half. Yeah.
yeah, log n by 2,
Yeah. Yeah.
or whatever the, yeah.
Yeah.
So the n, so when you sum up all these bits, because there are n bits, the maximum sum is going to be log n. Let's say floor of log n, right? And you just have to check whether this is greater than log n by 2, right? And sorry, not log n by, so what am I saying? So this is actually, you want to check whether n by 2, but the string is a log n bit string.
Yeah. Yeah.
So this is n by 2, but this is a log n bit string.
You have to check if the sum is greater than n by 2,
Yes.
n by 2, and that can be done by just checking the bits at the positions
Yeah.
log n by 2 onwards. Yeah.
Yeah. So I mean, you can just do the same, the greater than equal to thing that we first saw, right? We saw that even for n-bit strings, given two n-bit strings, whether x is greater than y, you can do this. This belongs to
Constant.
NC1.
Yeah.
In fact, belongs to AC0, but it also belongs to NC1. So just the only thing that was missing for us was how do I sum up these things to get this log n bit string, right? But now that we know that iterated addition is in NC1, this measure, we know that this is this summing up this the iterated addition of 1-bit numbers, this is in NC1. So you can produce this summation xi. Let me call this string y. So this can be every bit of this string. This string can be produced in NC1. That's what I claim. I mean, that's what follows from the fact that integer iterated addition, this is an NC1. Right? So even here, what did we show? We said that every bit of this iterated addition of n-bit numbers can be obtained in NC1. Right? So similarly, for the majority, you can just sum up the bit of this one single n-bit string and then get this log n bit string, and every bit of that log n bit string can be obtained in NC1. Yeah, is it clear?
Yeah.
Okay. Yeah. So now, so now we know. So what do we know? So together, this gives NC1 compose. So you can just stack up these circuits. I mean, like you have x1 to xn, and so maybe so there is this NC1 circuit, and what does it produce? It produces some log n bit string, and then you can also have this log n bit string for n by 2. Right?
Yeah, and you
And
just
then and then you just feed this to this greater than equal to, right? And clearly this is also in NC1. Yeah, NC1. So this is again another log n depth. So totally this shows that majority belongs to NC1. Okay, so all right, so so there are other ways to see this, and I like leave this again as exercise for you to read. I mean, this is probably but a little hard. So you can also, so if I had an n-bit this thing x1 to an array, right? So you study these things called sorting networks. So if I can sort this, right, and then produce another string such that it all contains zeros and the ones are at the top, then if I just go and check the n by 2th, then again I know the majority, right?
Yes.
So this is again another way to do it, and there are like a lot of these, for example, the sorting network, AKS sorting network, the famous sorting network. This actually can be implemented in NC1, but this is like using a like whatever a nuke to kill a fly. I mean, this is like because it's a very strong result, which in itself is like a I mean, very technically hard result. There are other ways. For example, there is this very amazing work of Valiant in the 80s. He showed actually, in fact, so see the majority function. It's a monotone function. Majority is a monotone function. So what do I mean by that? So so if I take a string, if I take an input right to majority, and let's say I change here, there's one, so, if I change a bit from 0 to 1, then the function value will not change. It cannot become 0. We cannot. So for example, let's say for this input, the majority was 1, right? And in this particular input, this position was a 0. Now, if I flip this, make this 0 into a 1, of course, majority will not change, right? Majority will still stay 1.
Yeah.
Right? And this is exactly a monotone function, which means that sort of like if you as you increase argument like a bit from 0 to 1, the function cannot decrease, right? That's a monotone function. So majority is a monotone function, and it is known that if you have a monotone function, then there should be a monotone circuit computing it. Should have monotone implementation. Let me just put it that way. Monotone implementation. So what do I mean by that? Well, without using any negations in the middle and so on, because the implementation that we just saw here, it might use a lot of negations in the middle, right? Because they're composing a lot of circuits. But actually what Vaishnavian showed that there is this monotone function also has a monotone implementation, and he came up with actually a randomized construction which works. So there is like he showed in fact he showed that there exists it's a it's a order log n depth circuit, and the circuit is actually very strange. What it does, it randomly samples a 3-bit majority function, match 3, sort of like it just samples 3 bits, computes majority 3 bits, and recursively it does this, and right, so it produces some n by 3 bits here, and then it keeps doing this. And then when it shows that this works, this will work, this will give you the right answer with a very high probability. And de-randomizing this is a very, very nice open problem. Like people don't know whether you can get deterministic constructions out of this.
Okay, so this is a randomized construction. The sense that the circuit you produce this way
is a randomized.
It will accept with a high probability majority.
With a high probability. Yeah, exactly. So
and if it is non-majority, then it will reject.
Yes, with a high probability. If the majority of the strings are not, the majority of the bits are not 1, then it will reject it.
But that is also with high probability. So it's not like it's not like it is sound.
Yes, it's sound. Yeah. So this is again another construction for majority. So there are many constructions for majority known. So in NC1 constructions for majority known. But yeah, so anyway, so we can, so for us, like now we have to, and I think like probably maybe I'll just say what is to come tomorrow. So what we are going to do is to show that NC1 circuits, what is the relationship between NC1 circuits and branching programs? Branching programs of constant width. Okay, so in fact, we're going to show that this is actually the same. They are going to be the same, and yeah, so, and this is the main theorem, and this is called Barrington's theorem.
You are saying that branching program can compute of constant width can compute majority.
Yes, that's, yeah. So that's like to answer the question in affirmative, what we saw before.
That is also a polynomial size, yeah?
Yes, polynomial size, exactly. Poly-sized, and so yeah, of constant width. And remember that like we saw that constant width captures the space, so constant width is like constant space. So this is like a way of saying that you can compute majority in constant with using constant space, provided you are given a lot of non-uniformity. But yeah, in fact, the circuits, the branching programs, in fact, that we construct are going to be actually very uniform. In fact, like they're not non-uniform; they're very uniform. Like you can actually, I'll talk about that tomorrow. One amazing thing is we still don't know how to get any. I mean, like yeah, like a majority in constant space, an algorithm which doesn't go through this whole thing. In fact, what we'll prove is that a much stronger result, will show that majority in fact reduces to a regular language. Yeah, in fact, it's going to be a word problem, some sort of a word problem. In fact, we'll do all this in the next.
Okay. Yeah. So then maybe I'll ask my doubts tomorrow. Because
Okay.
yeah.
So, no, you can ask today as well. Like I can. That way I
Like
can.
yesterday we said that
Yeah.
there is a relationship between
Yeah.
constant space s and width 2 power s.
Yes.
Yeah. In other
Yeah.
words, log w width means space w.
Yes, but this stuff is not. I mean that S. I mean, so there I think there are certain things which I threw under the rug. But yeah, so I mean, in the constant setting, I think because there's constants involved in the.
But what I don't understand is that if when I say constant width,
Yeah.
does this theorem imply that there is a constant space algorithm for computing majority?
Yes, that's what it means.
That's very strange, no? Because you have to somehow count the ones and
Yes.
counting, and
Yeah.
counting means that you need log and bits. Yeah.
Yeah. Exactly. Yeah. That's why it's a very surprising result. I mean, like it's a very surprising result.
So that's phenomenal.
Yeah, it's amazing. I mean, like it was, I think, voted the most surprising result in complexity theory in like a few. I mean, I think like a decades or something. I think everyone conjectured that this is. I mean, the original idea was to prove a lower bound. I think. So I'll tell you the story about this, how this. I mean, this guy, it was in his PhD thesis. I think first he proved some lower bound for small width, and then he was hoping for a lower bound, but instead ended up proving an upper bound. Also, like it's philosophically says why proving lower bounds is like sort of like hard because you don't know something like crazy clever like
Yeah,
this.
exactly. Yeah, I mean, if this could happen, then I can believe that a P can be MP.
Yeah. A lot of people say that, like use the same argument that like if this can happen, then who knows, maybe P equals NP. So
Yeah,
it's
like this is totally counterintuitive, but you don't need space. You just need constant space to compute majority. Is totally counterintuitive.
yes. Yeah. Indeed. Yeah, it's a very amazing result. So we'll see this tomorrow.
All right.
Okay. Okay, maybe I'll stop sharing my screen.
All right. Yeah.
Oh,
Okay.
sorry, I didn't switch on the video. I didn't notice that. Sorry.
No problem.
Oh, okay.
All right, then how is the weather there?
Oh, I'm in. Are you still recording?
Yeah, maybe.